Chapter 7 is all about clouds and precipitation, a little bit of weather radar, and our driving question here is how do clouds and precipitation form? The chapter opens with a case in point that describes how jet contrails that come out of planes can cause cloud cover. So you probably have noticed this if you live over an area where there's a lot of air traffic, like we do in Arizona. There's a lot of air traffic on the way to and from Los Angeles and Phoenix, and so you see these contrails in the sky. Sometimes you see them developing as the plane's flying over, and if atmospheric conditions are right, the contrails will stick around. Instead of dissipating, they will stick around, and they can actually spread out and develop into high-level cirrus clouds that end up having an impact on the local radiation budget, how much solar radiation is getting in, and how much long-wave radiation is being emitted. So you can read about this at the chapter opening to learn more. Cloud formation occurs through adiabatic processes, which we've talked about already in this class. A cloud is simply a bunch of water droplets, so a bunch of condensed water. So most of the water that's in the atmosphere we know is water vapor, but when that water vapor reaches its dew point temperature, clouds can form. So as the temperature and the amount of humidity in the atmosphere promote more saturation, the closer we are to that saturation point, the more likely we are to see clouds develop. So here is a reminder of the adiabatic cooling process. So as an air parcel is forced to rise, it expands and cools, and if it cools to its dew point temperature, then clouds will develop when the water vapor contained in the air parcel condenses to form little cloud droplets. So we call that dew point temperature that's reached the level of condensation. And you see this in clouds in the sky. There's kind of like a layer, a flat layer that the clouds are sitting upon. So that's the level of condensation. If you do an experiment in the laboratory with saturated air and cooling it to its dew point temperature, you don't necessarily get clouds developing for a number of reasons. One of the reasons has to do with this thing called curvature, which you can read more about in the textbook, of a water surface. So if you think of a tiny little droplet of water, the smaller the droplet, the rounder the droplet's going to be, and the rounder it is, it changes the properties of that water to interact with the environment. We call this the curvature of the water surface. So in a lab, things don't always behave the same as they do in the atmosphere. And one of the differences a lot of times in the lab is you can create a super clean environment, whereas in the atmosphere we have lots of little bits of debris in the atmosphere. We call these nuclei, which is the plural for nucleus, because they form the nucleus of clouds, the condensation droplets that form. So when the water vapor reaches its dew point temperature and it wants to begin to condense, there has to be a surface onto which the water vapor can condense onto. So if you're down at the Earth's surface, there's plenty for it to condense onto. That's how we get dew form, as I described to you in the previous chapter. But up in the atmosphere, there's no big flat surfaces like that. We just have lots of little debris. And those debris can be from any number of sources you see here: volcanic eruptions, wind erosion of soil, forest fires, ocean spray. All of this puts little bits of debris, ash, salt, little bits of soil, and so forth up into the atmosphere. And these are teeny tiny. They have little bitty radii. The radius is about a micrometer. So we're talking microscopic level here. But it's big enough for water vapor to condense onto. So once the condensation begins on a tiny little surface like this, it can continue to grow in ways that we'll talk about a little bit later. So we call these cloud condensation nuclei, CCN. It's just a surface for condensation. We can also have ice-forming nuclei, which are IN, designated by IN. And these promote ice crystal formations to form. So this would happen perhaps higher up in the atmosphere, where instead of vapor becoming liquid, we could have it become ice crystals. So a freezing nuclei is just it's a surface on which water would first condense, and then it would freeze when it reaches the freezing point. And then there's lots of different ways we can describe these nuclei. Deposition nuclei is simply if the process for the condensation goes from water vapor directly to ice. So in other words, it skips out on the liquid phase. We call that deposition, and the nucleus that gets deposited onto is called the deposition nuclei. So you can read more about these in the chapter. A special type of nuclei is hygroscopic. Hygroscopic means water-loving, and it refers to a chemical attraction that certain nuclei have for water molecules. A good example is salt, magnesium chloride, in ocean spray that is hygroscopic. It attracts water to it. And when you have these kind of nuclei available in the atmosphere, you're going to see cloud formation happening more readily. So the saturation point doesn't quite have to be reached. It can just be higher levels of humidity. You see here with magnesium chloride that clouds can develop with relative humidity as low as 70% instead of 100%, which would be saturation. So if you have hygroscopic nuclei, it's going to be easier for clouds to develop. Another example are cities. There's a lot of different types of cloud condensation nuclei over cities because of all the pollution that's generated, all the debris. So there's an abundance of debris over cities, and therefore a lot easier process of cloud development. And some of those bits of debris, some of those nuclei are hygroscopic, and so we get cloud development, and with cloud development always comes the possibility of precipitation. So because of all the different microclimates going on with a city, we can add to that list extra cloud growth and the likelihood of precipitation. Supercooled water refers to water that is still liquid below the freezing point of water. And this can happen, it's been studied to happen, because when water gets to that freezing point, say 0 degrees Celsius, there has to be some kind of mechanical action to actually promote the formation of ice crystals. So some kind of stirring, or in the atmosphere, the wind has to be blowing, or there's got to be some updrafts or something going on to really help promote that freezing process. So if there's nothing happening to promote that process, it's possible for water to drop down below 0 degrees Celsius and still remain liquid. Supercooled water nucleation refers to the process of nuclei forming in supercooled water. So if water is supercooled, how does it then form as a nucleus? What actually causes it to aggregate into a frozen state? And there's two ways here. There's homogeneous nucleation and heterogeneous nucleation. Homogeneous just means everything's the same, so it's just pure water. So if we imagine we have pure water, there's no foreign particles in it, and those foreign particles may be acting as ice-forming nuclei. So none of that, it's just water. Then it's possible for this pure water to drop down really far below the freezing point, down to, you see here, negative 39 degrees Celsius. This is called the Schaefer point. And then if it goes lower than that, then it will start to nucleate, to freeze. And so this is homogeneous nucleation. Heterogeneous nucleation, same process. We have supercooled water, but this time there are some foreign particles involved, or the water comes into contact with some particles that will serve as freezing nuclei, ice-forming nuclei. So if you introduce that, then you have the likelihood that you're going to have nucleation occur. but the water won't have to dip down to that Schaefer point, to that drastically low temperature. It'll be somewhere between there and the freezing point. And then these IN will form the nuclei that causes additional freezing to take place. So once freezing has occurred, it's much easier for it to continue to develop. Cloud classification is outlined in the book in a lot more detail than what I'll go here. There's a couple of tables you see that describe cloud classification. The basic classifications have to do with height in the atmosphere of clouds, as we'll see in just a moment. And then from there, they can be classified by their appearance, how they look, their temperature, their composition, is it ice crystals or water droplets, and so on. So here's another table that breaks down cloud classification, some more unusual cloud names, and their meaning and how that's applied. Let's take a look at this graphic, which shows cloud classification as a function of height in the atmosphere. So you see here the different heights in the atmosphere. So this first line shows us to be at about 2,000 meters or 6,500 feet above the surface, and then the next level goes up to 7,000 meters or 23,000 feet, and so on. So we have low clouds in this first tier, middle clouds in the second tier, and high clouds in the third tier. And you can see the different types of clouds and the way they look. So down here in the low cloud area, the lower part of the atmosphere, we have clouds that look like maybe stratus clouds. Stratus means layer. So typically stratus clouds are extensive. They cover a very extensive part of the sky, but they tend to be pretty thin. So if you've had the experience of flying in an airplane and there are stratus clouds in the sky, so that when you look up at the sky, it's overcast. You don't see the sun typically with stratus clouds. When you go through the plane, you see it's a very thin layer of clouds, and then up above it's a beautiful sunny day. So that's a stratus cloud. Stratus clouds can also be associated with rain. So another designation of stratus cloud is nimbostratus. When you see this nimbo, it comes from nimbus, which has to do with rain. So rainy stratus clouds. So they can be a little bit thicker, but still not very thick, still contained in the lower atmosphere. And the precipitation that would come from this type of cloud would be kind of a steady, light rain, not thunderstorm, just a steady, persistent kind of gray day rain. Also in the low cloud area, we have stratocumulus. So getting into cumulus clouds. Cumulus are the fair weather clouds. They're the kind that you typically draw when you're a kid, the light little cotton ball type clouds. And then we can use that word cumulus to describe the appearance of other clouds like stratocumulus, a combination of stratus clouds and cumulus clouds. So you see some cumulus development here, some cotton ball type development, but it's got that kind of overcast sky look that comes with stratus clouds. Cumulus clouds are individual. They are like little cotton balls. So they're just like little puffs of cloud. And cumulus clouds can grow. They're formed by updrafts, and if the updrafts continue to develop, then you can get vertical development with these cumulus clouds. You get something called cumulus congestus as that cumulus cloud continues to grow. And then if it continues to grow from there, we end up with something called cumulonimbus clouds, these gigantic thunderstorm clouds. So again, that nimbus word, the Latin word that we saw with nimbostratus, here with cumulonimbus, these are cumulus clouds that have really developed all the way up through the troposphere to where they top out at the top of the troposphere, at the stratosphere. And they are associated with thunderstorms, severe weather, hail, and so on. So they all of these clouds start, and most of them stay in the lower atmosphere, the low cloud zone, except for cumulonimbus, which is the towering giant. In the middle level here, we have the word alto applied to our clouds. So alto cumulus, alto stratus, combinations of these other types of clouds that we've seen, alto referring to the fact that they're mid-level. So mid-level clouds tend not to be as dense as the low-level clouds. They can still be quite extensive and cause a mostly overcast sky, but they tend to be a little thinner, so you can still kind of see through them a little bit, or a lot, as the case may be. So altocumulus have the cumulus formation. You see the individual cumulus type of formation, but with the alto appearance of this level of the atmosphere. And then altostratus is kind of a thin, wispy's not the right word, just kind of a thin see-through stratus, thin because it's at that alto level. And here's a typical thing you see over the sun. You can still see the sun through the cloud, but it's not clear. It's not a clear day. So this is typical of alto level clouds. And then finally, the high level clouds, because they're higher up in the atmosphere, it's much colder up here. And so these clouds are based on crystals, ice crystals, instead of water vapor. So here we have the word cirrus applied to the clouds. So cirrus refers to these wispy clouds. So here's a straight cirrus cloud. They're just kind of wispy, high-level clouds. And then at this level, if we have cumulus clouds, we call it cirrocumulus. So tiny little cumulus formation, but with this cirrus appearance of very high-level clouds. This is what's referred to as a mackerel sky. If you've ever heard that old sailors saying, the mackerel skies at night, sailors delight. Mackerel sky refers to these cirrocumulus clouds. And then cirrostratus, again, we have kind of a stratus, so a layered type of cloud that just kind of covers a large portion of the sky, but very thin. So here, like we saw with the altostratus, you can still see through them. You still see the sun, and even more so than you did with the altostratus. But you may also see a circle, a halo around the sun. It may look kind of rainbowy. And a lot of times with these cirrus clouds, you do catch little glimpses of rainbows in the cirrocumulus or even just in the straight cirrus. And that, as we'll talk more about later in this class, has to do with the fact that these are ice crystals up here. And the ice crystal can diffract the sunlight in ways that cause it to break it out into its individual visible light components. So these are your basic cloud classifications. I encourage you to read more about this in detail in the book and practice. Look out in the sky and make yourself identify what types of clouds you're seeing. There are some special types of clouds we'll talk about next, starting with mountain wave clouds. So when you have a mountain, it disrupts the airflow because of the topography. So if air is flowing in the direction that you see it here, when it encounters a mountain, it's forced to rise up, and it causes these kind of ripples in the atmosphere. And these ripples end up causing the air to rise up a little bit, and if there's any water vapor in the air, which no doubt there's some, if it rises up to its dew point temperature, you'll get clouds develop at these high points and the ripples. So the disruption to the airflow due to the mountain causes cloud development to be more likely. So these types of clouds that form at the ridges of these ripples and the airflow downwind of a mountain are called mountain wave clouds. So these are lenticular clouds. You'll hear that term for like a lentil, the little bean. It's lens shaped. And they sit right over a mountain. So here's a picture of Mount Rainier, and you see some lenticular clouds that have formed in this wave pattern because of the airflow. There are also something called banner waves. These are another type of mountain wave cloud that extend downwind of a mountain peak. So it might be kind of instead of individual little tufts of clouds, a consistent string of clouds that are downwind and the disrupted airflow. Another wave type of cloud forms with a stable atmosphere right between the interface of the two layers of air. So in this case, our layers of air would be dense cold air and less dense warm air. and the warm air wants to stay on top of the cold air because it's stable. But we have movement happening, and the movement will likely be happening at different speeds because of the density and the different properties of these air masses. So because the warm air is less dense, it will be moving faster, and over time, as this movement continues, you start to get a little bit of disruption between, or where the two meet at that zone. So this vertical shear, this is called shear when you have winds moving at different directions or different speeds in this case. It causes this disruption, which if it develops over a long period of time, you can see these little waves that develop, these cute little waves. So here's a picture of the sky with these kinds of clouds. Probably you've seen these. A very rare type of cloud is called a Noctilucent cloud. These form in the upper mesosphere. So we're very high up in the atmosphere, about 50 miles high, and you really only see these at high latitudes, so as you're close to the poles. And what happens is because it's very cold up there, we have ice clouds that can form when there's just very little water. So it's possible for that to happen, though it's not very likely. So here's an observer standing somewhere on the Earth, closer to the pole. And here's the nighttime, so the sun has already set for this darker portion of the green, and the sun is still visible over here in this part of the Earth, so it's shown as a lighter color green. So if the sun's still shining over here, some of the rays are able to reach the higher parts of the atmosphere where our observer is. And if there are any of these clouds forming high up in the atmosphere, they're going to be very thin and very scant, but at this time of the evening for the sky, or the night now, the sunlight can shine on these noctilucent clouds and make them illuminated for the observer here.